All right, let's talk about number 3 on practice exam 3-1. This is the one where we're looking at some research from Dora Carrico-Muniz from Wellesley, and we're focused on, in the first part, transforming this alcohol into this ester, right, which is angel marin, which is the target of their synthesis. All right, so when we look at this to try to do the synthesis, again, we should break this down into things that are a little more simple than looking at these complicated molecules. I know sometimes it's easy to get overwhelmed looking at these complicated molecules, but your goal is to break this down into simpler things. And so I hope that we can look at this and relatively quickly figure out there are only a couple of things that are different. Right? So if we focus here, we're going to react that alkene, okay, and then the other thing we're going to do is to react that alcohol. So we're going to take the alkene to an alkane, and we're going to take the alcohol to an ester. Right? That's all that we're doing in this problem. Okay? And we know how to do those reactions. We know how to take an alkene and turn it into an alkane, right? H2 catalytic palladium. And we know how to take an alcohol to an ester. We just have to react it with an acid chloride. So two relatively straightforward reactions can enable us to make this really complicated material over here. Right? So let's do those two steps and then see what it looks like. Right? So if we think about the order we want to do these in, there's an alkene over here, so we may not want to introduce that before we do the hydrogenation, the H2 reaction. So it may make sense to do the H2 reaction first so that we don't introduce another alkene that we can react the H2 with. Right, so let's say first we should do H2 catalytic palladium on carbon. And then we can write out what we should get. Now, one of the parts of this question is what potential problems are there? And hopefully it's clear there are two potential problems in doing this reaction. One, you have an alkene here, but you also have an alkene up top in that ring. So you could potentially react with that alkene as well. That could be a problem. And the other problem, if they want to make only this enantiomer of angel marin, you have to get the H adding only from the back. Right, what that also is a potential problem. So those would be the two potential problems in that step. Right, and we're nearly done. All we have to do now is take this alcohol and turn it into an ester. And again, when we think about making esters, remember that you're making that bond, so the O comes from the alcohol. And so we can think about the acid chloride. That's just the other piece of the molecule. Right, so there's the acid chloride that you want, and to avoid any problems, you may say that you want to add pyridine in there just to have a base around to react with any HCl so that doesn't cause any problems for you. Right, so again, alcohol, acid chloride, that's going to give you the ester. Right, potential problem in this reaction would be if two of these molecules came together, you could have the alcohol over here react with the acid chloride of another molecule, and then that would give you a dimer of this, just a different ester that you wouldn't want. Right? So that's a potential problem for this one. But in general, I hope that we're getting comfortable with these more complicated molecules and not getting intimidated by them, just seeing that these are straightforward reactions that we've done on simpler molecules many times. All right, the next part of that problem is looking at this molecule, right, and trying to figure out how many stereocenters we have and to label them R or S. Right? So when we look at this molecule, we should identify that we have 1, 2, 3 stereocenters. Right? Those are the only centers that have carbon attached to 4 different atoms. And then assigning RS. Right? So let's label this as 1, that is 2, that is 3, and we'll look at each of them separately. So if we look at the center that's labeled 1, right, so this is 1, so we have nitrogen going to a carbon, down to a carbon, and then to a carbon over there. So that's clearly group number 1. Now I think we're going to have to do a table to figure out what's going on. right? So if we go to the right, and then down, and then left. Okay. So we go to the right, we hit a carbon attached to C and H and H. If we go down, we hit a carbon attached to carbon, carbon, and then H. And if we go left, we hit a carbon attached to carbon, carbon, and H. All right, so we've identified that going to the right is going to be the lowest priority. All right, so we figured that out. Now we have to figure out whether down or left is going to be 2 or 3. So down we were here, then we go out to here, so that's attached to a carbon and then another carbon from the alkene and then an O. So that was going down, so it's carbon, carbon, O. We were out at this carbon, so we can go to the next carbon, right? And that's going to be carbon, H, and O. Carbon, H, and O. So because of that, down is going to be the highest priority, and left is going to be second priority. So that'll be 1, or sorry, I get that mixed up. That's going to be 2, and that's going to be 3. Right? So down's going to be 2, and to the left is going to be 3. So if we do that, that one's going to be R. Okay? And again, we have to be methodical going through these because they're not always that easy to do. Right? So then number 2, we have all carbons on this one. H is going back, which is nice. Right? And so then we need to figure out what's going on. So we'll do another table. So if we're going up, down, or right, because we're all connected to the carbon. So up would be to here, so that's going to be carbon, carbon, carbon. Down is going to be carbon, oxygen, hydrogen. And then right is going to be nitrogen, carbon, carbon. So that one's not too bad, right? The oxygen is going to give us number 1, nitrogen number 2, and then the other one's number 3, right? So down is 1, to the right is 2, to the left is 3, right? So that one's going to be S, okay? And then number 3, that one, we have oxygen coming out, H going back, and then 2 carbons, so we have 1, 4, and then if we look out, just one more, we can get this one done because there's an oxygen here. Right, so we have 1, and then 2, and then 3, right, so 1, 2, 3, so that one's going to be S. Right, and again, if we just work through these methodically, we should be able to do these without too much trouble, but you have to take the time to do it methodically. Otherwise, again, you might as well just flip a coin. All right, so the final part of this problem is comparing this structure to the structure given over here. Right, and so I think it's useful just to step back, take a look, and see what happens. If you take this molecule, right, and you try and rotate it to overlap the rings out here, you can see that it doesn't overlap really well like that. I think the thing that's most useful is if you imagine taking this one and you rotate it this way and you line it up, hopefully you can see that that's a mirror image. Or if you take this one and just sort of rotate it and bring it like this, you can see that it's a mirror image. Right? And if you look at all of the stereo centers, OH is coming out, nitrogen out, benzene out, and the 5-membered ring back. They're all the same. So if you look at these, and again, you take your time to try and rotate, mentally rotate, you can see that this one is a mirror image. All the stereo centers mirror perfectly what's going on in the other one, so this must be an enantiomer. Okay. And if you wanted to, you could go through and assign R and S, and if you did that, you would get that they are all opposite. Right? But I think that one's much easier doing sort of mental manipulation.